So let us start here. I'm delighted to introduce Héctor Muñoz-Avila. Héctor is an associate professor of computer science at Lehigh University. He's also the NSF program director for the program on robust intelligence. He works on a large number of very interesting things. I have known Héctor for about 15 years now. Yes. So he is a leader in case-based reasoning and in planning and decision making. He publishes frequently at AAAI and HCI, which are two really hard to get into conferences. He has been the director or the chair, co-chair of IAAI, which is Innovative Applications of Artificial Intelligence. So that's another very prestigious position. So I'm going to keep my introduction short, but I'm delighted to introduce Héctor.
Thank you, Ashraf. So can you hear me? Okay. I usually speak loud, but it helps to have the microphone. So thank you very much, Ashok, for the invitation and for I have some wonderful meetings so far. Very impressive campus, I should say. This research that I'm going to be talking about is, when I say we, this is really the royal we. There are a number of people at different institutions that have collaborated with me, as well as a number of graduate students that have worked in my lab with me. As Ashok mentioned, I'm a program director at the Robust Intelligence Cluster. I manage the AI and the machine learning portfolios. However, today I'm going to talk on my behalf, not for the foundation. So just to make clear, whatever I say, Héctor says, not the foundation says. The topic is goal-driven autonomy, specifically expectations and self-monitoring systems. So my plan today is to give a general overview of my research interest. Then I'm going to dive into the research problem of this presentation. Then I'm going to talk about this technique called goal-driven autonomy. I will use GDA, goal-driven autonomy, indistinctly the two. Then I'm going to demonstrate how GDA was used for a real-time strategy game. Then I'm going to talk about the focus of my research group in GDA has been automated learning of the knowledge needed for these GDA agents to work. And finally, I'm going to make some remarks, including next steps and future research directions. So let me talk generally on my research interest. I work on areas on reusing episodic knowledge, case-based reasoning, generalizing and abstracting knowledge. So it could be used in many different domains and problems, which is machine learning tries to do. Using that knowledge to solve new problems, which is planning, acting in an environment, executing those plans while there is environment that might be dynamic, that's agency. And finally, the agent introspectively reasoning about his own actions, that's called cognitive systems. Also very interested in applied and collaborative research. I created this chart that shows my an overview of my research interest. I have some theoretical contributions, systems built, and some courses that I regularly teach. They are interconnected, and the talk today is centered around this continuous monitoring and planning, which is related to the AI game programming course that I frequently teach. So let me talk more about the motivation and the research question for this work. So you may have seen in the past few years there has been a big press, and this is probably bad press, on AI, and here AI is treated, robotics, machine learning, anything related to intelligence has received bad press. There has been well-known people, including renowned physicists, who have warned about AI. They have, again, covered in a number of magazines, including Newsweek. And there are people from computational background that also have done similar warnings. So it has received a lot of bad press, and there is some concern about that. I'm not going to directly tackle those larger concerns of whether the AI is going to take over the world, but I'm going to talk about a problem that is still challenging, but is something that is more concrete and probably we can help tackle, and is the problem of autonomy becoming more common more agents are being used in different places, and as a result of that, there have been unfortunate situations. Last year, or actually 2 years ago now, in the Volkswagen plant in Germany, they had an accident. A worker was activating a robot, and this robot became active and unfortunately pinned the worker and killed him. It turned out that this is not as uncommon as one may think. There's an article in the New York Times reporting several cases of robots causing some accidents. In the 2013 roadmap for US robotics that was coordinated here at Georgia Tech, they point to the need of safe robot behavior. So that's on the robotics, but it's not really limited to robotics. You may have here a few years back, somebody hacked into Twitter and put the false news that the White House had been attacked. There were 2 explosions and President Obama was injured. There are these automated trader agents that reads these feeds from Twitter and then automatically started selling stocks, and they'll cause what is called a flash market crash, and they had to actually stop trading for a moment, make sure that people know that it was not that was a false news. But nevertheless, this example shows that the need for these robust capabilities of the agents, and unfortunately, because agents are going to become more common, this autonomy, we're going to see more and more of this. So these are just a few examples. I imagine 5 years from now, I'll have a full slide with many, many different examples where autonomy has caused some problems. So the research question that I'm interested is trying to investigate agents that are aware of their own limits and boundaries, what we call self-assessment. They recognize when they have a step out of bounds, so they are self-diagnosis, and finally they are able to act to bring themselves back within the required working parameters, so that's self-correction. So that's the general area that I am interested. Goal-driven autonomy, which I'm going to explain next, has been a technique that has been developed trying to address some of these problems. So the overview is you have a planning system that is generating plans, and you have this GDA control on top of the system evaluating how the planning is going, monitoring the execution, and make sure that everything is working according to plan. So the GDA agent controls the focus of the agent planning activities and is resolving discrepancies online as they occur. It's intended for complex environments where one is making real-time decision-making. That includes situations where the agent doesn't know all of the information that is going on in the environment. There is partial observability. Situations where the agent is interacting with other agents in that environment. Actions that the agent perform may have multiple different outcomes, so they are stochastic. The updates that occur in the environment are dynamic. That means there are changes that happen that are independent of the agent's own actions. And finally, the goals are dynamic. The agent may need to change the goals while operating in the environment. So the key concepts of GDA, and this is the standard architecture, we have the notion of expectation. The agent knows what is supposed to be the outcome of his own actions. And the agent is constantly supervising if the observed outcomes are different from the expected outcomes. In that case, there is a discrepancy, a mismatch between the expected state and the observed state. When a discrepancy occurs, then the agent will generate an explanation of why that discrepancy happens. And as a result of that explanation, he will generate a new goal. So this cycle keeps repeating online while the agent is operating in an environment. Some considerations: we need to compute this expected state. We need to compute the mismatch between the actual and expected state. There are multiple inferences mechanisms that one could use, which is great, but the downside of that is that if they are very expressive, inference can take a long time, and it's supposed to be operating in real time. Computing explanation requires to reason about inferences made in the past. And finally, reason on alternative goals require the agent to project what is called dead reckoning, project into the future what will happen if he tries to pursue different goals. So all of these things are requirements for a GDA agent to operate. So this is our overview of our GDA research, and I said several people involved here that I mentioned in the first slide. We created a first GDA system using rule-based. I believe that was the first publication where this term GDA was coined. Then later on, we relaxed this condition of having a rule base to have a case-based reasoning, knowledge-based. It was more flexible. Still, we were not happy with it because all of these cases had to be created manually. So later on at ISCA 11, we presented a system that is capable of learning most of the GDA knowledge. And that was later extended in an article on artificial intelligence. Then we demonstrated GDA on a real-time strategy game. More recently, a few months ago, one of my PhD students, Dustin Dannenhauer, had an ISCA paper where he defined this notion of informed expectations. I'm going to define those carefully in a moment. Not carefully, but I'm going to informally define those. And in a few weeks, we are going to present work on metacognition and GDA at AAAI. So that's a brief overview of what we have done. In this presentation, I'm going to show a few aspects of this research. So to try to ground things, I'm going to give an example of an application of GDA. And this time it's an application for playing real-time strategy games. So I'm not sure if you are familiar. Let me talk a little bit about those. So real-time strategy games are adversarial games between two opponents. Each player controls some units and controls some buildings. The player is harvesting resources, and those resources are needed to produce units, buildings, and research new technologies. Those new technologies allow the player to construct more powerful units and more powerful structures. And the objective is to destroy the opponent units. What you see down there is a collection of types of units that are used in one of these real-time strategy games called Warcraft 2. I'm just mentioning that because perhaps the students would recognize that name. And what is interesting about these kinds of games is that they follow these rock, scissors, paper models. So unit A of class A might be very powerful versus a unit of class B, but very weak versus a unit of class C. So part of the strategy here is to create a balanced army to counter the opponent. To give a sense of scale, I want to illustrate a few differences between real-time strategy games and chess, which is probably an example of a game that we know well. In chess, we know the board is 8 times 8. In a game like Warcraft, the size of the board is 128 times 128. The branching factor on average in StarCraft is 200. On average, a player can make 27 moves in chess. On average, in Warcraft, a player can make 800 moves, 700 moves, whereas in chess, an average game will have 80 tops moves. The player will control in a Warcraft up to 100 units, whereas in chess, he will control 16. Decision gaming is real time, and that means I am playing versus you, and if I am faster, I can make 3, 4, 5 moves at the time that you're making one, and that's allowed. It's real time, so speed is rewarded. And it's partially observable, so you only see part of the map, whereas in chess, obviously, you see your pieces and you see the opponents. So it has all of these interesting complications. So we created an agent to play these kinds of games. So the way it works is as follows. There are 2 layers. At the bottom layer, we have specialized agents that make localized decisions. At the top layer, we have the GDA agent, which is telling these specialized agents what is the next goal they should try to achieve. So we have two threads, the GDA thread making high-level decisions, and the agents thread making low-level decisions on how to play the game. So here is a schematic of the architecture. We have here the GDA layer, which is looking at the environment. This is a snapshot of the game. It's looking at the environment. And it's telling these specialized agents what is the next goal that they should be pursuing. These agents are all reinforcement learning agents that are interacting in the environment, trying to maximize the reward. As you can imagine, the reward here is simple. It's simply the difference between our score and the opponent's score. We are trying to maximize that difference. And the agents are operating that way. So these are the specialized agents. I mentioned that there are different classes of units. So we have one agent that controls all of the units in that class. So for example, we have the agent called peasants. Peasants is a kind of unit that is used to harvest resources and to build structures. So there is an agent that manages all peasants in the game. There is another agent called knights, manage all of the knights. Knights are a melee unit that is very powerful versus archers, but very weak versus pikemen, and so forth. We have, I think, 8 or 9 agents, each specialized in one kind. So they're executing actions based on the goals that they receive, and they receive a reward from the environment and keep this process. So how these specialized or individual agents operate. And this is an example execution. So in these games, frequently, the rules are each player starts with one peasant and one town hall. That's it. So typically, a player will build a farm. So this is a timeline from left to right. It will build a farm, that peasant, and that farm allows to produce more units. In the meantime, that town hall, the only purpose of that is to build peasants. So we'll build a peasant. At this point, the town hall will have no resources, so it will do the do nothing action. Do nothing is an action. It's a decision made by the agent not to do anything in that while resources are collected. That second peasant that was constructed will start building a barracks and so forth. So it gets many more units are being produced. All peasants are controlled by the same agent. The town hall is controlled by a separate agent. Barracks is controlled by a separate agent. Footmen, which is a kind of melee unit, is controlled by another agent, and so forth. So I'm going to show you a quick video. On the left side, you're going to see the GDA agent. On the right side, you're going to see the agent controlled by the AI in the game, Wargus, which is a clone of Warcraft. This is a small map, 40 times 40, and there will be a forest separating the two opponents initially. So initially, there will be no combat until that forest is removed by harvesting wood. So let me show you the video. There is no sound, so I'm going to be talking myself about this. So it starts with one peasant, and the peasant builds farm. It's going at a very fast speed for the purpose of the video. This is down hole. This is the gold mine. It's used to harvest gold. It has 3 or 4 peasants already in action. They are constructing more farms, allowing to build more units. They are starting to harvesting wood, so they're starting to remove that obstacle. Here is the building AI on the right side. Those are the green orcs. So they're harvesting more. In the meantime, the game AI is doing the same thing. The building AI also harvesting wood on the other side and producing more units. So now I start to produce military units. This is one footman. The separation between the two is almost gone. Now there is combat because the two units come in contact, from the opposite teams come in contact. The GDA agent is trying to control the center of the map. It works in chess and it works in this game too, controlling the center of the map, so it will control most of the resources. And from there is slowly destroying the opponent economy by destroying buildings. At this time, those people who play the game will know that red is going to win because it's producing more units and the other one is losing more. So now it's a matter of time until the GDA agent wins. I think is done now. So that's just a quick example of system after training. We did some experiments comparing evaluation study, comparing how the performance of the agent works when they are without any GDA control and how they work versus when you add the GDA control on top of them. And we have some experiments. Yes?
Does each party has the big picture and knows everything, or is it
it doesn't have the whole picture. Oh, for this game, yes, the map was turned on for us to see, but the agent only, the rules of the game still operate. It will only know where the units are.
Not
So
the other
no, so it uses something called the fog of war. So when the player will only see what is within range of his own units. If the player moves a unit away from a location, it will still know the topology, but it would not know whether enemy units move to that. And that's still in place here. We turn the fog of war off just for visualizing what's going on, but it was, for the point of the agency, was still on, so they could not see.
So is information important in this game? Do people
Absolutely.
send spies? Or
Absolutely. So it's very important because if I know, for example, that if I knew that my opponent was building majority of one class of units, I could use that by producing the counter, and then it would be very easy to defeat. So part of the there's a little bit of game theory principles here, because I have to speculate what is the opponent doing and trying to counter based on that. Somebody who may follow this more closely knows that Warcraft is not the state of the art in computer versus computer. There is a more difficult game called StarCraft. So there is another competition, computer versus computer, using a game called StarCraft that's more state of the art. It has the same, what game theoreticians call the same constitutional rules. Both of them have the same operation, but StarCraft is more complex because it has more different classes of units, and the maps are larger. So it's interesting to talk a little bit about that. It's illustrative of the difference. So I call AI, what we call here AI, hopefully everybody in this room. But when people in the game industry say game AI, that's something completely different. That means any algorithm that plays the game, whether it's using any AI, reinforcement learning, planning, that they don't care, as long as it plays. So the competition is currently dominated by game AI, meaning this hacking into the programs, as opposed to what we will call AI. I have a lot of interaction with people who do research on or participate in the competition called general game playing, and another on the Atari 2600, and they complain that all of these competitions are dominated by Monte Carlo methods. And I hear that, I said, I wish I was in that situation, because at least you are tweaking an AI algorithm, doing Monte Carlo search, tweaking parameters. Here, when we have tweaking here is tweaking the procedure so we'll produce 4 peasants instead of 3. Is that level? So there is a big gap there in terms of the AI and the game AI.
So you mean they cheat?
No, they don't cheat, but they hard-coded. So there is no, like, a search. I will do some learning and see patterns of my opponent and see what I will do. They will follow a straight strategy. So initially, so for example, people know from experience that it's better to start building the second peasant first and start harvesting gold as opposed to harvesting wood. So they will hard-code the program, so they will have that opening strategy that from experience has been shown to be very effective. So it's hard-coded programming as opposed to trying to find patterns and trying to do game theory. What happens if I try this? So right now, that's the state of this competition is like that.
So is the distinction between using knowledge and programming it directly and AI very clear? Or is it blurry?
No, it's very clear. So I teach the game AI course, and I know when I'm talking about game AI, and I know when I'm talking about AI, right? So I can.
What's the proper definition of that border?
Oh, you're killing me. So
That's my question, right?
The game AI part, you're tweaking the algorithms themselves. You're tweaking code, hacking, to get certain desired behavior. On the AI side, you have these general principle procedures.
But if I write rules, I'm also tweaking the AI.
Right. You can tweak the procedure by modifying code, but in the case of game AI, I am tweaking the code directly without any care of what procedure is going on in the background. Whereas the people who are doing like GGP, they are maybe tweaking code, but they are changing parameters for this Monte Carlo search, so it will do more exploration instead of more exploitation.
And that becomes AI.
That becomes AI. Yeah. So
the MetaLevel has a complete model of the local agents?
yes, the MetaLevel has a model of the agents. Yes.
The model is complete and correct.
The model is it knows. Actually, I take that back. The MetaLevel is knowing what the actions are that the agent each of these individual agents are performing, and it knows the rewards that the agents is receiving from the environment, and it knows the information that is passed to the agents. Actually, it doesn't know the black box of the inner workings of the model. So I take that back. It doesn't know the inner workings of the agents. It only knows the information that is being passed back and forth. And it's learning based on that. There is something interesting. We know that the best AI, or game AI, is able to defeat the best human player in chess. That happened some years back. It's well documented. So it will be interesting to know what happens in a game like StarCraft. So there was an exhibition game last year between the player playing StarCraft, number 50 in the world. I forgot to mention, there is an annual professional league of a StarCraft player. If you were in Korea, you will know that actually thousands of people go to a stadium to watch this game in big screens. There's a huge follow-up. So there is a professional ranking. So we had this exhibition where, there was a conference, they had this exhibition that they brought number 50 player, which happens to be actually the highest ranking player outside of Korea. It's a fellow who lives in Seattle. And they play it versus the best AI, the winner of the computer versus computer competition. And what happened is, basically within 10 minutes, the human player was easily defeated the best computer opponent. And to illustrate how easy it was, if you have a game of two players that are around the same level of skill, you will see that it will take like 40 minutes for this game one of them to win. And there are parts of the game that if you're watching the game, you will get very electrified and very tense of what is going to happen, because you know something. When we saw this exhibition game, and it's available online, it was like a no contest. The human was easily tricking the game AI. It took 10 minutes. And it was no contest from the beginning. That, despite the fact, remember I mentioned that this real-time game? The AI was giving commands 3 times faster than the human opponent. So for every command that the human player was making, the AI was making 3 of those. And despite that, within 10 minutes already finished the game, but within 2 minutes, 3 minutes, we will see that the AI was nowhere near. So those of you who are in graduate school looking for a research project that is challenging, here is one open, creating human level competitor for this game. So let me, yes.
Has there been a test against a novice human StarCraft player? I mean, I guess there have been, but
Oh yeah, you can do that test yourself. Meaning you can start the StarCraft game, which is a commercial game, and they have these you can play versus the computer on a map that you design, and if you're a novice, the computer will defeat you very easy. When the 50th player in the world is really somebody who has really played many hours per day. These are professional leagues. The best players earn about $1 million or $2 million every year. So this is, those people who play seriously, they really are professional. Anyway, I'm going to change gears now. And I'm going to talk a little bit of the focus of our research group has been on having these GDA agents work great, but they require a big knowledge engineering effort. So a big question there is always with where does that knowledge come from? All of the explanations and planning knowledge and where does it come from? That has been the focus of our work, our group. So this is the GDA cycle that I showed you before. So let me highlight that image. So one of the first questions is, one of the first inputs for this GDA system is the planning knowledge. You need to be able to generate plans. We use a particular, not only we, but other people use a variant of planning called HTM planning, hierarchical task network planning. So it has further requirements in terms of knowledge engineering that is required. And we have worked on generating that HTM planning knowledge automatically. So let me first explain what HTM planning is. HTM, or hierarchical task network planning, is a planning paradigm where you are giving complex tasks as inputs. Those tasks are decomposed into simpler tasks using some knowledge artifact called methods. A method will indicate how to decompose a task into subtasks and the conditions required for that decomposition. Once these tasks have been reduced to very concrete level, they can be achieved by operators, which are actions in the domain, indicating how to transform the domain based on the actions. So the knowledge engineering requirement here are the operators for performing the actions and the methods. So the learning HCN knowledge problem can be defined as follows. You're given a collection of task descriptions, meaning the preconditions and effects of the tasks, and you're given a collection of plans. They could be, for example, in the context of the game, we have observed a player playing a game and we have those traces. So those are given to the input, and the problem is to learn these methods and operators. So our algorithms that we have developed operate as follows. If you're given an execution trace, so each of these squares correspond to an action, we are given the task, preconditions, and effects. We identify the states where preconditions are met in that trace, and a state where the effects are made, and then we hypothesize that task is accomplished by this sequence of actions. So in this particular example here, we may have a task that we call T prime that is accomplished by this trace because these preconditions of T prime are valid here, and the effects of T prime are valid here. So I construct a method M prime for that. So that question is then, okay, fine. So given a trace, I can construct the task, but where do the task hierarchies come from? How do you need two or more levels? And that comes from the following. I may observe for the same trace that a subsequence of that is achieving another task. So in that case, the learner will say, well, task T prime can be decomposed into task T. A special situation is when task T prime is equal to task T, then we learn recursion. So the agent is able to learn this recursive method. So we have explored two different kinds of methods, symbolic and a statistical. In the symbolic, we use a well-known technique called goal regression, which has been developed many years back. And we created an extension, something we call vertical goal regression, because as we are learning these hierarchies bottom up, then we need to regress the necessary conditions, that we call vertical goal regression, and we learn methods that way. The other one is a method that we have explored is statistical methods we take the traces and we generate constraints from the traces. So just to impress you, I have here a formal constraint, but let me loosely indicate what that constraint says. That constraint reads the following. If I have a segment of a plan, and that segment achieves a condition, okay, it's called P there, and that condition has some parameters, and those parameters are a subset of the parameters of a method, then I'm going to hypothesize that that condition P is a precondition for that method. So we are using constraints like this, we generate multiple such constraints, and then they're given to a weighted max hat solver, a max constraint satisfier, and it's weighted because if we observe the same constraint multiple times, that will have a very high weight. If we observe a constraint only once, that will have a very lower weight. So then when we give this to the constraint satisfier, it will generate solutions. For example, it will say this condition is true, meaning indeed that precondition will be, that condition is a precondition of the method, and others will be discarded. So I mentioned there are these two methods. Statistical methods allow us to learn not only the methods, the composition of task into subtask, but also the actions. So they are very powerful in that regard. The symbolic techniques that we have explored only learn the methods, but not the actions. On the flip side of that, we can formally prove that the knowledge learned, the methods learned by the symbolic ones are always correct. Any plan generated using those methods will always be correct, whereas the statistical methods will have always a small error rate, and in fact, they have to be tweaked manually by the human. In an artificial intelligence paper some years back, we showed that the cost of doing that correction. So that's as much as I will say about this learning knowledge, but it's possible to learn the planning knowledge automatically based on input traces. Yes?
Question. It almost seems like you have a chicken and egg problem here, in that if you take the plan trace and break it down into pieces, you can look at those pieces and see what are the necessary preconditions and effects that happen to those pieces. But you sort of need those preconditions and effects to know where to break your trace in order to have these actions. So how do you decide where you break the traces?
Great question. I'm going to just backtrack a little bit to answer that. So in the current definition of our problem, we are assuming that we are giving as input the task descriptions, meaning the user, before running the algorithm, will give preconditions and effects of the tasks. Now notice that that's a subset of the conditions that are observed in the state. So let me give you a concrete example. In a transportation domain, we may have as precondition that for a task, transport this package to this location. I may have as precondition that the first parameter has to be a package, the second parameter has to be a location. And as effect, I will have the condition that the package is in that location. When we are navigating through the traces, we have states that are telling, oh, there is package in this other location, but it's a package, and then that's the thing that will be identified here. And in this one, we satisfy the goal of that package being in that location. That's where these segments are identified. I guess the follow-up question is, maybe you will identify many different traces, right? Segments. If my conditions for the task are very loosely defined, I may identify many. And this statistical method that I mentioned down here is great for that, because fine, you just take as many as you can, give it to this constraint satisfier, and it will find the ones that are more common. Yeah. So once we have learned this planning knowledge, it comes the question of how we can elicit expectations automatically. So that's what we have been working on that recently. Typically, so let me give you some conventions that I use for this presentation. I have a plan, a sequence of actions. Each of these squares is an action. The brown actions represents actions that have already been executed in the environment. The blue actions are actions that we plan to execute, but have not yet executed yet. So we have planned for that but not executed. So the first kind of expectations that has been explored in literature is something called immediate expectations, which always looks at the conditions of the next action that is going to be executed. So we'll check if the preconditions are valid in the observed state, and after executing the action, if the effects are valid in the observed state. That's called immediate expectations. That's a very frequently kind of expectation used in the GDA literature. There are other kinds called state expectations, where what you do is you start in a starting state, and you project forward the state by using the action definitions, and then you compare whether that expected state that is being moved forward is satisfied in the observed state. Those are state expectations. We have goal regression, which looks at the planned actions, the things that we have not executed so far, regress from the goals, and look backwards. What are the necessary conditions to execute the plan that remains to be executed? That's called goal regression. There's a way to define that. And very recently, Dustin he introduced what is called informed expectations, which moves forward, but it doesn't move the state forward. It just moves the conditions that have been executed so far from the plan. So there are some properties that one could observe. Immediate expectations will guarantee that the next action will be valid. So it guarantees, next action will be valid, but it's myopic in the sense that 5 steps ago, I might have taken control of a zone, or some region in the map, and I'm assuming I am controlling that region. I'm continue planning, and unknown to me, the enemy has taken control of that region. So I'm planning ahead, making this assumption that my plan is going well, when in fact it's not. State expectations certainly take care of that because it's looking at the complete observed state, so we'll make sure that every step that region that we took control 5 steps ago is still under control, so it will not fall in that situation. But on the other hand, any change in the state will be causing a discrepancy, and there might be changes in the state that are not really relevant for my current plan. So there is some region somewhere in the map that may change of hands, but it's really not relevant for my current plan, and it will cause a discrepancy. So they are overreaching. Goal regression are the best ones in the sense that they really guarantee minimality. These are the minimal conditions that are needed for the rest of the plans to be executed. The problem is in a dynamic environment where the plan may change, then the conditions that are checked here might not be correct. So the informed expectations, they basically guarantee that doesn't matter how you complete your plan, as long as it's a completion of the current plan, those conditions are the conditions that need to be checked. They are not wonderful in all situations. If you are executing the same plan, they will be overreaching too. There will be checking conditions that are not necessary for the current plan. But if the system is dynamic, informed expectations will work quite well. I have here the formal definition of what is that. Let me explain to you. No, I'm not going to do that now. But this is built on a HTM planner called CHOP, developed by Dana Now at the University of Maryland. I was doing my postdoc at the time, and I was part of the team that developed. And those of you who know CHOP would recognize that a screenshot immediately in the underlying parts are the parts that we modified to compute these informed expectations. So let me show you just graphically how these are computed. Suppose this is an HTN. As usual, the square represents actions. The circles represent tasks. And typically we go left to right, compute the conditions that are moved forward by the first action, continue moving forward the next action until we generated all of the conditions by actions that are achieving the first subtask. So now we can define the next subtask. We continue forward for the next subtask, left to right, and we get that, and we continue the same process for everywhere. And that's how we compute it. We did some experiments in some domains that are used in the GDA literature. For details, see Dustin paper at ISCAI last year, where we showed that these informed expectations indeed work very well when the environment is highly dynamic and you need to change the plan over time. The next question is, how will one generate an explanation? What is even an explanation in this setting? So for that, we assume we have HTM plans, and now we have the means to generate them and learning knowledge for that. We assume that these tasks are annotated with expectations. We now have the mean to generate those expectations automatically. The additional knowledge requirement here is we assume there is an ontology. For the gaming domain, ontologies are freely available. So if you look at the manual of the game, they will explain that the knights and the footmen are melee units. You have to be in close range to fight one another, whereas the archer and the cannon are range units. So they have this ontology of the kinds of units, so that's easily available. We define discrepancies as inconsistencies induced by the ontology. We define explanations as the conditions for those inconsistencies. I'm going to exemplify these two concepts with an example. So this is a top-down view. This is now the game of Warcraft. On the top right, bottom right side, you have the starting base. In the opposite end, the opponent's base. And this is implementing something called a double envelope maneuver. This was invented 2,000 years ago by a famous general called Hannibal. He was fighting a famous Roman general. And this Roman general had this powerful formation, and Hannibal had this idea of attacking the flanks simultaneously while weakening the center, and that ended up being a famous Battle of Cannae. And we basically had implemented in an HTN that performs that same maneuver. By the way, well, it was 2,000 years ago, but it's still in very much well used today. That same maneuver, not only in games, but in real battles. So two flanks and attack the enemy at the same time. This is the HTN that captures that strategy. So here is first flank on the brown, second flank, and now attack at the same time. It assumes that it has these, so they have these task decompositions, and we have these expectations. The main condition here that is needed for this to work soundly is that if you have an expectation from an upper level task, that has to imply the expectation from the lower level task. This work, by the way, predates our work on informed expectations, the one I just explained, and informed expectations meet this property. So it was perfect that we were able to generate it that way. And now I'm going to explain it. So typically in GDA research, and even when I introduce the concept of GDA, I explain it using the traditional definition. We have X, the expectations of the agent, and S, the observed state. And I said a discrepancy occurs if there is an expected condition that is not observed in the state. That's the standard definition. In our work, we use the ontology, and given the observed state, we generate all of the facts that are that can be inferred from the observed state and the ontology. And then a discrepancy occurs if this inferred state, when united with the expected state, is inconsistent. And you can use a number of inference engines to generate that. And the explanation is the collection of facts used to generate that inconsistency. So here is an example of one. We have as expectation that the player controls a region. A player controls a region if all of the units in that region belong to that player. On the other hand, using this inference, we're able to show that the region is contested. The same region is contested, meaning that there are units from the player and from the opponent player in the same region. So these two facts are mutually exclusive. That's what generates the inconsistency. And the explanation for that is precisely that there are units from the opponent and from our team in that same region. So we did some experiments showing that with this ontology and this definition, you get better results. I will not go into details, but refer to this case-based reasoning paper last year. Last year, yes. The final topic is learning the goal formulation knowledge, how we do that. So you generate, the GDA cycle says you generate an explanation, and once the explanation is generated, one needs to generate the next goal that should be achieved as a result of that explanation. So we end up modeling that as an MDP, it's a Markov decision process, reinforcement learning, where the states are the explanations and the actions are the goals that needs to be achieved. So if you are in a particular, you generate a particular explanation, there are multiple goals that could be achieved, and basically use the feedback environment of reinforcement learning to select the expected values of those goals and select the best one most of the time. The main problem is that there are many possible explanations, so this NDP will be humongous large, and it will be not workable, so we use case-based reasoning to reduce the size of the states. If two explanations are very similar to one another, we'll treat them as one. And that end up working quite well. For details here, is paper 11. Some related work. Many people have done work on agents. I want to recognize Ashok and Bill Murdoch. I mentioned, somebody asked me a moment ago about this notion of tasks having preconditions and effects. We borrowed that from TMKLs. So that was like perfect for our work. Their work on planning. For example, there has been many works on plan repair. This has been a standing topic for many years. The difference between plan repair and GDA is that in plan repair, you are executing the plan, there is a discrepancy, and you try to repair the plan to achieve the same goals. Whereas in GDA, one may change the goals altogether. And there has been a lot of work on learning. So I come to the final part of my presentation. We're going to talk about the future work and final remarks. Up until now, you have seen that my research on GDA has been on these virtual environments, the synthetic words. I did my sabbatical 2.5 years ago at the University of Trondheim with a group that is using AI to predict failures of deep ocean drilling for oil. And simultaneously, I had started some collaboration with civil engineering and electrical engineering colleagues at my university, Lehigh, looking at using of this agents technology for problems that they have. So we were awarded an SF CyberSeas grant on wave energy conversion, which seems completely different from what I've been talking about. I'm going to explain the connection. Unfortunately, I had to exclude myself of that grant because I was named program director, so I could not be a researcher for my own agency, so I had to preclude myself. But let me tell you what was that work about, and this is still ongoing. So they are taking, they're producing energy from waves, and they have these what is called wave energy conversion devices, or WECs. They have many of those. And the problem, when we got together, the problem that they described to me that is very difficult for them is that there are many changing conditions for these devices. So the weather changes, there are changes from day and night, season changes, hurricanes, and all of these things that may happen. And it's very difficult to program a priori all of the potential things that may happen over time. So then I suggested that we could look at each of those devices as agents using a theory developed by B.S. Subramanian. He showed how you can take a piece of software and convert it into an agent, and we have done some work related to that. And then our challenge will be in these domains. Unfortunately, many of the information is continuous, so the signals are continuous, not this nice discrete, you have 10 peasants, now the signal is a continuous function. So so that's where an interesting challenge for me is, and that's really where I'm moving towards that direction. Doing this GDA, but on physically grounded environments. So they have these conditions like continuous modeling. Fortunately, there have been, as you know, tremendous advances in statistical machine learning, things like deep learning and convex optimization that have been shown to be very sound to deal with these approximations. So I see an open field on doing these high-level AI and cognitive systems like GDA, but embedded in these physically grounded environments, and that's what I'm going to start working next as soon as my stint at NSF ends. So with that, I want to just finalize with a quick summary. I have showed you this goal-driven autonomy cycle that enables agents to self-assess, self-diagnose, and self-correct. I exemplify this on a real-time strategy test bed that has some of the complications that make applied GDA research interesting. I have shown the focus of our group, which is on learning and generating this GDA knowledge automatically. That includes learning planning knowledge, generating expectations, generating explanations, and learning goal formulation knowledge. And for future work, I want to concentrate on GDA systems in physically grounded environments. And with that, I want to thank you. Yes.
Hi, my name is Alicia Ravinsky. I'm with Lockheed Martin Advanced Technology Laboratories. This is really interesting work. It makes me think with respect to work that I've done in terms of course of action generation and editing. And I like how you mentioned grounded versus just real world systems, because this adds a specificity to what you're talking about.
Yes.
But have you thought about applying this technique, this planning and revising sort of the state analysis and impact of state on your plan? Have you thought about applying this strategy, this approach to course of action in a military sense?
In a military sense?
Yeah.
I have not done recent research on that, but on GDA, but in the past I do have worked with a colleague from the Naval Research Lab, his name is David Eha, where we had looked at the problem. They have this problem of they have these sensors built in these Navy vessels, and they are accomplishing some mission, and then there is some contact, sonar contact. And there is a question there of what should they do, right? So should they abandon what they're doing, explore the contact, or should deviate from their current trajectory and find something that is safe? So that's certainly an area that this kind of grounded physical environment where you have sensor information. And here remember, this ping that's on the sonar may be nothing, right? Maybe actually a false alarm. But on the other hand, you cannot consciously ignore it and say, oh, that might be nothing, let's continue. So definitely I see a lot of room for that kind of research, and that's the kind of thing that I want to do, but I have not done that yet in the context of GDA. We did this context that I mentioned, that we did it in the context of applying case-based reasoning for physical environments, and then we had these pre-generated plans storing cases, and we had these discrepancies, and then we were doing replanning. What I mentioned, replanning, you still have the same goals and modify that. But in the concept of GDA, that's things I would like to do next.
I have one other quick question, more specific, technically. When you were describing the properties of your expectations, the immediate expectation versus the state expectation, the term discrepancy came up when you were talking about state expectation. But I was wondering if a discrepancy can emerge immediately, if you're taking an action that just doesn't produce the effect that you expected.
Correct. If I didn't mention discrepancy in the context of immediate, that was a mistake. When there is an immediate expectation, the agent checks if the preconditions are valid in the observed state before executing the action. And if not, there is a discrepancy. And after executing the action, it checks if the effects of the action are still valid in the next observed state, and if one of those conditions are not valid, then there is a discrepancy. So for all of those four kinds of expectations, there is a discrepancy. It's just that some check localized and some check more general. Yes?
So you started with some motivations from robotics, and I wanted to get a sense of how these RTS games strategies were related to the robotics in the real world problems, and things like path or action planning in robotics, which are continuous and physics-based. Is the nature of the uncertainty and of the discrete actions very different that prevents you from using this, or is this the same domain?
Right. When I said I want to move to physically grounded AI, that includes I want to move to robotics too, because in the game setting, when I say it's partially observable, that means my units cannot see where the other units are until you remove this fog of war. But there is no sensor problem there. Once the unit moves there to a location, you will know exactly what are the conditions in the map. And of course, when you have sensors, that's simply not true. You get these continuous signals, and one is not even certain that what is that object, let alone saying, oh, there is an orb close by. So there's a whole different, there's a mismatch in the assumptions there. And they had this, I mentioned the oil drilling, they had the same situation, the inputs there, I'm sorry, I remember, they have these continuous functions. They actually, in the oil drilling, it's even more complicated because they're not observing the state, they're observing the function outputs of the state. So they're observing these functions. I want to move into that direction next, the problems here with the games are making the assumption that basically sensory information is not a problem, which in real situations, in grounded situations, it is.
Does you explain why your prior work is not directly applicable to this kind of robotics planning? My question was on the positive side. What of this is directly applicable? What lessons or techniques?
Right. So the whole notion of discrepancy. So there is a notion of discrepancy there as well with sensory information. I can see and perceive that there is something that I was not expecting. So I could at least know that there is no object that I expected, and with some level of uncertainty. I have to reason that. So I have to extend the environment, same cycle, but now I will have to introduce belief values and some uncertainty values to these conditions. But it's basically the same cycle. You have things that you expect the robot to see, discrepancies between what the robot is perceiving and what is expected. And need to replan, generate new goals based on that.
So, for example, a robot may want to grasp something and guess where the center of mass is. Then, at the first attempt to move it, discover that it's not the case. Is it similar, or is it different?
It is. In fact, I mentioned David, one of my collaborators. I have not done research on that, but he has done some work on GDA for robotics, and that's indeed the situation. So they will do the cycle, but with these uncertainties and belief values. So you have to introduce probabilities in that case, just because there are uncertainty in what you're seeing, and therefore there has to be uncertainty in the explanations that you provide, and therefore there is uncertainty on the goals that you generate.
I can ask Alex question a different way. What are the scope conditions here? So because you have real time, you have partial observability of the environment, you have non-deterministic environments going on here. So in some sense, there is a degree of generality here.
Yes.
You mentioned two scope conditions. One is uncertainty. There might be noise in the environment. So you have to introduce some way of tackling that noise. And the other is where the data is coming continuously, not coming continuously. Is complexity also a problem?
So when we add these probabilities, then that adds a level of complexity, because now when I'm planning, I have to plan on where I believe that I am, as opposed to where I, in this other context, I knew where I was. So if I am in the game setting, I know where my units are. In this sensory setting, I believe that I believe I know where my units are. So there is some level of uncertainty, and that adds a level of complexity. So I can respond in this way. In the planning part, I was talking about hierarchical task network planning, generating a sequence of actions. In this setting, if I am lucky, the solution will be either an MDP or a POMDP, because I am partially observable. I'm partially observing the environment. I believe in a particular situation, and I am planning accordingly. That's a partially observable MDP. And that's the kind of planning that will be needed here. Planning on where I believe it I am. Yes?
I was wondering if you've been working with any collaborative applications, because this whole expectation discrepancy model could be a good formulation for teamwork. So having expectations of what is your teammate is supposed to do, how you're jointly accomplishing goals, etc.
So the real-time strategy game in a way is a collaborative setting, because remember I mentioned there are these 10 agents. So each of these agents are making their own individual decisions. And the GDA level on top of it is passing these goals. So in that context, there is a collaboration going on there, because these 10 agents have to collaborate with one another, and that's done through the GDA. Yeah. It's difficult to have an agent that will make all of these decisions centralized. In fact, I mentioned that there are these hard-coded agents that are the ones that are really used in the competition. And when you look at the code, they actually have these individual pieces of the code that are taking care of specific components. So even though it's hard-coded, they have this flavor of multiple collaborated agents, but it's hard-coded.
Other questions? Last one.
Yes.
So where do we stand on real AI, not game AI, playing this Warcraft game versus game AI of humans? Are we going to win?
Yeah, so hopefully yes, if we are the good guys, right? Yeah. So the military application, that's what somebody else was asking in the back, of this kind of technology is very important. So many of these autonomous systems are they need real-time decision making. So there is this defense system called the Aegis system. It's a Navy vessel that is specialized in destroying incoming missiles. And one will think that's a decision that should be made by a human, but actually not, because they have the time frame is seconds. So they are working on this scenario where there are many incoming missiles, and they will hit Navy vessels within seconds. So you need this rapid decision making and rapid reaction. So there are multiple real situations, even in this minute, where you will really need this kind of autonomy, is simply because, if there's a human, it needs to wait a minute, what is going on, and then decide what to do. By that time, the missile has already hit.
I was asking you to the Star Trek game you mentioned, or is real AI competing there? Not yet.
They are hard-coded. And not really using AI. There is a caveat that I have to make. I mentioned that there is an opening that when the game starts, you start with one worker in one building, and there is this first 10 minutes of the game you're building that economy, and that's an optimization problem, right? So what are the next steps that I should do? That's before you encounter the opponent. Actually, that opening was developed by a reinforcement learning algorithm. And all of the players, human players, they probably not the reinforcement learning, but they follow the steps. And when you see these high-level competitions, when people who are playing that, they follow the same opening, and that opening was created by an AI agent. So it's the other way around there.
Let's thank Hector once again.
Thank you.